Good evening, everybody in India, and good day to everybody else outside of India. So this is our IEEE-GRSS Bangalore section talk in the series called the Bhoo-Mandal talk series. So this is our 14th talk since its inception. So we'll start now. So today's talk is how can AI help climate action? And we have Dr. Kalai Ramea from Planette. She's joining from the US. Briefly about the talk series and the chapter, and then I will hand over the stage to Mr. Gurudatta, who is the secretary of the chapter, and he will introduce the speaker, and then we'll move on to the talk. So a little about the Bhoo-Mandal talk series. So this has been initiated by IEEE-GRSS Bangalore section. It's a public talk series which started in the middle of the pandemic, so in July 2020. Its aim is to educate, enthuse, and inspire citizens about all aspects of science and engineering, advances in Earth observations and remote sensing. Bhoo means earth and Mandal means sphere in Sanskrit. So these talks touch upon various aspects of geoscience and remote sensing, including technology, society, policy, etc. We have a series of the talk on our YouTube channel. So this is a playlist that we have been maintaining, and we do get several views on that. So it's been going, and you can see the variety of topics we have covered and the variety of the diversity in the speakers we have had as well. So this is briefly about IEEE-GRSS itself. GRSS is Geoscience and Remote Sensing Society. This is a 1-minute blurb that we have.
GRSS is the IEEE
Geoscience
and Remote Sensing Society.
Our mission is to build a community of researchers and practitioners by means of knowledge sharing and scientifically rigorous dissemination of the latest advancement in remote sensing.
The technical committees are really meant for doing the technical outreach to other parts of the research community and industry.
We want to inform our members and reach different communities via different channels, like for example social media, journals, and especially education.
At the moment we have more than 60 chapters and 20 student branches all over the world.
I love GS family very much, and I'm very honored to be the member of it.
Being part of GRSS allows me to be a better researcher and professional, improving my skills and knowledge to do a good job. Come and be part of this great family. Ciao!
So I'd like to give you a brief about IEEE-GRSS Bangalore section. This is a society chapter in Bangalore, and it was started in December 24th, 2012. So we just completed 10 years. So it's a big milestone for us as well. So I'm Jaya Srivasanar. I'm with IIIT Bangalore. I'm the chair of the section of this chapter. Dr. Shamlal from NIT Surathkal is its vice chair. Mr. Gurudatta from Veridas, he is the secretary. And Dr. Nagajyoti from NRSC, he is the treasurer. So those are the office bearers. And we have a larger EXICOM committee where student chapter office bearers are ex officio members along with advisors. And we have several young professionals who lead several initiatives at the chapter. Now, for student chapters, we have 3. NITK was started in 2021. MIT Manipal was started in 2022. And NIE Mysore just started in 2023. So this is sort of a snapshot of the number of members we have. So we have been steadily growing. So we grew from 59 in 2021 to 75 in 2022. And if Gurudatta can give the numbers, it is probably close to 100 right now. And yeah. And the gender ratio is fairly good, actually. And we have a good diversity in terms of the stages of professional growth, that professional stages that the members are at. We'll just give you a brief overview of the activities that we do at IEEE-GRSS Bangalore section. These activities are funded by the IEEE-GRSS Global And our activities pretty much include student events, which are hackathons, mapathons. We have workshops, we have summer winter schools, and talk series like the Bhoo-Mandal talk series. We have distinguished lectures series, which is funded and run by the IEEE-GRSS Global. And we have several panel discussions, etc. This year has been very particular. We have taken the plunge into conference organization, and we have a big conference, which is the IEEE-GRSS 2023 coming up. Before that, I'd also like to give you a brief overview of IEEE Connect 2023, which is the flagship conference of IEEE Bangalore section. And we are running a track at the IEEE Connect. The track is going to happen day after tomorrow. So I think IEEE Connect registrations are still open, and they have a variety of different topics that they discuss and similar tracks on them. Ours is track E on cyber physical systems for geoscience and remote sensing. Our EXICOM members, Drs. Ujjwal Verma and MC Chandan, are the track chairs. And we have around 5 papers that are being presented there. Dr. Chandan and Gurudatta are going to be serving as session chairs. So if you'd like to check it out, it is at Ramaya Institute of Technology tomorrow and day after. So this is a blurb about the IEEE-GRSS, that is the IEEE India Geoscience and Remote Sensing Symposium. This is a regional GRSS conference. And this is happening for the 3rd time ever, but the first time in a physical way, and it's in hybrid mode rather. So we will have some remote participation in case they cannot make it in person. We have a very vibrant technical program, so please do check out our website. We have several partners, so IEEE Bangalore section, Geospatial World Forum, Let's Talk Spatial, and Geospatial World Chamber of Commerce are currently our partners. We are going to be having a few more. It's work in progress. And the venue is IIIT Bangalore. And we have the MINRO, which is a government of Karnataka initiative at IIIT Bangalore sponsoring us. They are our gold sponsor. We have several more sponsors coming up as well. And as a quick flash news, Dr. Upendra Singh from NASA is a NASA technical fellow. He has agreed to give a keynote talk. Again, several keynote speakers are also in the pipeline. So please do watch out for more information on IEEE-GRSS in LinkedIn and all the Twitter. And so we keep posting time to time. So please watch out for that. So without much ado, I will pass the stage to Gurudatta to introduce our esteemed speaker for the day. And thank you, Dr. Kalai, for agreeing to give a talk here. Yeah, thank you.
Thank you, Dr. Jaya Nair, for a quick introduction about IEEE and Geoscience and Remote Sensing Society. It's indeed a very memorable moment for all of us as members of Bangalore section that we are taking the baton of hosting the Indian Geoscience and Remote Sensing Symposium. So I would request all the audience to take note of the website which Dr. Nair had posted here, and please go through the website and try your best to contributing to the symposium as a speaker or a paper presenter or anything, or maybe even spread the word about sponsoring the event or even getting involved as a volunteer in it. Coming to today's talk, I would give a very quick introduction about our today's guest speaker, Dr. Kalai Ramea. She is an accomplished interdisciplinary scientist. She is working in the confluence of artificial intelligence and science, and her research aims at leveraging cutting-edge technology like AI, especially to tackle problems for social good. And her primary area of focus is climate action, climate being a very sensitive and very key topic in today's activities across the globe. So it's very interesting to see that she is doing a whole lot of work in this context. Her latest achievement was leading a $1 million DARPA awarded project in collaboration with researchers from Canada and Germany. Her project focused on developing hybrid AI approaches for climate tipping points and interventions. Dr. Ramea has done her engineering from Anna University in Chennai. Later on, she pursued a master's degree from University of Southern California, and she has secured her PhD from University of California, Davis. She has published more than 40 papers in peer-reviewed journals and conferences. So I was very lucky that I could attend one of her talks in the recent past, and that kind of inspired me, and I was very eager to host her talk in Geoscience and Remote Sensing Society, and I'm very happy that Dr. Ramea agreed to give a talk, and we are very happy to listen to you. I extend a warm welcome to you, Dr. Ramea. Before we get you started, I just want to run through a couple of housekeeping points. All the audience, you can post your questions in the chat window. And during the course of the talk, please keep your microphone on mute so that we can get to hear Dr. Ramea talk about a very important and sensitive topic that's important for all of us. So over to you, Dr. Ramea.
Thank you so much, Guru Datta, for the warm welcome, and thank you so much for the opportunity to present here. Today's talk will be about AI for climate action. I thought of introducing myself, but Guru Datta gave a very nice introduction. So I finished my civil engineering in undergrad in India in College of Engineering, Indy. Since then, I finished my master's at the University of Southern California. I worked as a consultant, focusing on environmental and transportation research problems for 4 years, after which I decided to go back to school for getting a PhD in energy systems modeling. Since then, I've been at Palo Alto Research Center. So this is a legendary research lab in Silicon Valley, which was at the forefront of several inventions, including the GUI, mouse. So I had the privilege of working there as a research scientist, and later on I went to lead a group called Complex Systems Analysis, where I led about like 10 to 15 research scientists and engineers. We worked on several problems, mainly on how to use AI for social good. My focus was on climate action, as Guru Datta mentioned. I worked on several energy systems problems and climate action problems, and there were a few others who worked on healthcare. So I had the privilege to lead all of that. So since then, I quit Park 2 months ago. It's a very new venture. So I've been affiliated with Planette. It's our startup. So I'll talk a bit about that in the next slides. So the overview of today's talk. So I thought of giving a very brief introduction to AI ML techniques for those who are not aware, because that will set a stage to go further to discuss on how we could use AI for climate action problems. And how can we use AI for tackling climate change? So I'm going to give a few focus areas and an example, and specifically the one of the things, as Guru Datta mentioned, the DARPA project that we led. So I want to elaborate on that further, and some of the ethical and fairness considerations when using AI, because this is something very important. And then I'll talk briefly about Planette, our new adventure. So I want to give it not like a disclaimer, but more like a preview of this is not an exhaustive coverage of all the climate and AI applications, but just to give an overview to intrigue interest, because this is a new field. So climate scientists have been studying, obviously the geoscientists have been using remote sensing applications for several years now, but the use of AI techniques in climate and geosciences, it's relatively new. In the last few years. So there can be many applications, but I want to give a brief overview of how you could use these. But imagination is your superpower, so you can go ahead and do all of the other things that not talked about in this topic. So a few terminologies. So when we say AI, machine learning, many people interchangeably use it. So I want to give the definitions of what these are before we start using these terms. So artificial intelligence in general, it has been around for some time, that terminology itself. So it generally means ability of any machine to imitate human intelligence. And within that, machine learning has gained a lot of traction in the recent times, mainly because of the explosion of big data and the compute power. So the reason being, in artificial intelligence in general could mean a lot of things, like expert systems, which may not use a lot of data. But in general, specifically machine learning uses a lot of data. What it means is that the machine learns from data. And within this subset of machine learning, we use a term called deep learning that uses neural networks to mimic brain to learn that intelligence. So that is another new, relatively new field as well. Not so new now, but relatively new field as well, which has been gaining a lot of traction. Neural networks have been around for quite some time, but then the use of deep learning, like just adding more and more layers, just to learn from extensive amount of data, is relatively new. So when we use machine learning, it also includes deep learning. So just for the housekeeping stuff. And I also want to give like a very brief overview on the different techniques, because we will be discussing some of these. So there are mainly three kinds of algorithms that you use in machine learning. And the first is supervised learning. And forgive me if you already know all of that. I just want to talk about this before we get into the topics itself. So in supervised learning, you have a target data. So which means, say, for example, you're classifying between a cat and a dog. You have the labels named like cat and a dog for those images, and then the model learns the differences over time. It can be for regression models. Say, for example, you have like, housing prices. That's a very common thing that you use for linear regression. You have the target and the model learns from the target where that is going up and down. When we think of machine learning problems, like most of the problems fall into this category. Generally, people have labeled targets, the model learns from the data, and then it does what it can. Then we have unsupervised learning. This is generally used where you don't have the target and you don't know how to, or the data is large, like you don't know how to label them. So that's where we use some sort of clustering. Say, for example, you want to cluster the data into different groups that you don't even know to begin with. So that's where you start doing unsupervised learning. And if they have multiple dimensions, you use like PCA, like dimensionality reduction, to go from there. So next commonly used is unsupervised learning. And the other school of algorithms is reinforcement learning, typically used in robotics and other kinds of things, where the agent learns the system or the environment. So in this case, you give a reward and a penalty. Say, for example, if a robot is learning to navigate a maze, so you assign a penalty if it runs into a wall, or you assign a reward if it goes through without running into anything. So it's a very simple mechanism, but in general, like you can design a pathway for the agent to learn to navigate an environment by itself. So it can be used for many things. I gave robotics as an example, but you can think of like climate pathways, which, it's one of the things that reinforcement learning is being used for. So we can talk about that in a little bit. So why climate action now? So these are some headlines that appeared in the last month. So we are seeing record ocean temperatures that put the Earth in uncharted territory. So if you look at the chart, this is what 2023 temperatures of the global sea surface temperature looks like. We have never been in this situation before. Since then, like we have started seeing a lot of extreme weather events, be it like floods in India or in Vermont, USA, or extreme heat everywhere else in the world at this point. There are so many heat wave incidents going on. So we are getting into this crucial time where it's now or never. So we have to think about climate action now. And obviously there are like so many different techniques that's being developed for decarbonization, emissions reduction. But this is a very complex problem, because it has a lot of data, thankfully. And we need all kinds of help to tackle this complex challenge. So we get to climate action now and have a livable Earth as a result. Now that's where AI comes in. So it has a unique role to play. So the climate data sets are often huge. So obviously you're familiar with remote sensing data sets that you're getting from satellites. But when I talk about climate data sets, these are Earth system models that you get from running these scenarios and initial conditions of climate. When I say Earth system model, these are like physical equations that are run for each grid around the globe that are resolved at a given temporal and spatial resolution. These can be in the order of terabytes to petabytes. It has been a challenge for climate scientists to wrap around this and how to make sense of this data. And it requires advanced solutions. When I say it's a complex system problem, What it means is like you change one thing in the climate system, it affects so many different things because the atmosphere, the ocean, the cryosphere, they're all interconnected. So it requires sophisticated solutions. So it's not just you solve linearly and get it. It requires a lot of compute to do that. And to give an example, like the typical Earth system model, if you're running like a high result scenario, it takes about several weeks to months to just run one scenario. And that's the kind of computing problem that the scientists are running into. And thinking about AI, like where it can contribute, like it has made significant advances recently to tackle complex challenges. Mainly we are looking at in computer vision and more recently in natural language, like it has just exploded in the ways it can apply and the way it can deal with a lot of data. And we have access to high performance computing now better than ever. Like every year or so, we are seeing the use of GPUs and TPUs, even better than those. Like how can we use those things for different kinds of large scale science problems? So we are at a very nice place to tackle all of these things for climate action. So a couple of focus areas that I want to look into for today's talk. And as I mentioned, this is not exhaustive. You can always think about a lot of things. The first thing is computer vision. I think this will most probably be interesting to remote sensing scientists as you're dealing with a lot of satellite data. And then another thing is natural language processing. So typically that has not been the focus for climate, but then with the use of language models, this has been changing. Thirdly, data-driven optimization, and finally, physics-informed machine learning. The last one, the physics-informed machine learning, is something I worked on last year for the DARPA projects. I'll go into a bit more detail on what that is. So computer vision, I mean, it's a no-brainer. So the algorithms that we have for remote sensing and images, it can process vast amounts of data, be it satellite, be it like hyperspectral drone data or multispectral drone data. It's been widely used now, and the usage is only going to increase. The most common tasks are classification and segmentation. So when I say classification, it's just, say, for example, classifying between different land use characteristics, or even like segmentation is like delineating a forest cover area or land cover area. So these are most commonly used in these areas, but then, object detection could be also another. So with the availability of new satellites, so when I say new satellites, these are very high resolution satellites, think Planette Labs, or GHGSat. These are satellites that can even go until like 25-meter resolution for each grid. That's like super high resolution compared to what we used to have before. The possibilities are endless. So we can even think about combining different levels of data sets to actually extract information, which we weren't able to do before. Some common examples, forest monitoring has been, used by remote sensing scientists for many, many years now. But what the new techniques could do is, like, as I mentioned, the segmentation algorithms and the classification algorithms could be used to better analyze the data and do these tasks. One of the famous example is like the forest monitoring, where you can actually look at the size of the forest, whether there is illegal deforestation happening, or something else is happening with the climate change, the forests are like catching up on wildfires or drying up. We can monitor these over time. One example of where companies are making money out of remote sensing is like there's a company called Pachama. So the big companies, like the corporations, they actually buy carbon credits based on these forests. Say, for example, Netflix, if it wants to buy carbon credits for the emissions that it's emitting, they invest in a land in Amazon. But there is no way to know whether the forest that they are investing in, they're saying like, okay, this is the carbon emissions we are offsetting, but we don't know how it's going to happen in the future, like how it's going to change in the future. So the companies like Pachama act as this middleman. They use remote sensing and AI to look at these forests covered over time, and they make sure there's no illegal deforestation happening and that the land cover stays intact. And then they inform Netflix, for example, that's saying, okay, this is what you invested in, and this is how it stays over time. And if it changes, like, look, it has changed. prepare for like a backlash on greenwashing or whatever, like you need to invest more or invest less in things like that. And that has taken up. It's not just for forest monitoring. They do this for ocean monitoring as well, where people are now using kelp, which is like a seaweed. So they absorb carbon. So they kind of like people just dump the seaweed and then they look at over time like how it changes. So that's a huge area of growth that people are seeing right now. Another thing is coral reef monitoring. Not as much as remote sensing, but then this is more like underwater imagery. So as you know, like with climate change, the heat waves are happening, especially the marine heat waves are happening more and more. And as a result, coral reefs are at the risk of dying off. What this means is like it's a huge biodiversity criteria. Like, I mean, if the coral reefs are dying off, then it affects the entire marine life. So the Australian scientists are doing all kinds of things to preserve that. So one thing we can do is like, monitor them. The way the scientists are doing right now is they're taking underwater images. They look at the color, texture, and even the structure, and find some early warning signs if they're about to die off, and then they intervene, and then they make some changes, localized changes to the coral reefs so that doesn't happen. Another thing is air quality monitoring. Now, this has taken off in a huge direction recently, especially in the US because of wildfires. So, in India and Asia, like, the NOx emissions are huge. Like, that has been monitored for some time. There are satellites like Sentinel that can look at NOx data, and you can even like monitor that over time. And there was a very interesting study during COVID, how the NOx levels reduced because of the lockdowns. And the interesting thing that they're looking at right now is carbon monoxide due to wildfires. So that has increased quite a bit, when it happened in California, when it is happening now in Canada and the Northeast areas. So again, segmentation algorithms and even change detection algorithms are being used for air quality monitoring. And if you're implementing a new policy, these things can help and assess over time whether it's actually taking place, whether people are following the rules, whether the state is following the rules, and so on. Again, these can be at different levels. The one picture I'm showing here is from the satellites, but you can think about using drones for air quality if you're looking at very fine emissions, like from pipeline emissions. So you can still do localized drones and then do it. And finally, precision agriculture. Now, this is an area where the applications are just exploding. And mainly because, the possibilities are so huge in this area. So you can think about like crop monitoring, like weed or yield monitoring. So there are different levels of monitoring here. So either at the ground level where people take pictures and then they look at whether the plant disease, like what kind of disease is it? I think Google had come up with an application for that. Then at the drone level, you can see like, whether the water management practices are followed or the crop regulations are followed, and whether there are any major issues in there. And then at the satellite level, you can even look at the yield over time. Even prior to getting the yield, you can monitor it and see whether your land is going to make this much compared to last year and things like that. One of the biggest challenges is because of climate change, the practices that we know in agriculture are changing so much. So there are companies like Climate AI that looks into this specific thing. And then they suggest to farmers like, hey, look, in the next 10 years, your land is going to dry up too much. So this is not the crop that you would want to use. So things like that will help in the long run with the food security problem and all the crisis that comes with climate change. So the next is data-driven analytics and optimization. Now, this is very specific to sensors and like the Internet of Things. So what this means is that this is a very neat example for that. When you think of smart grid, you can think of so many different aspects to it. Think about smart houses that are within it. It has solar panels, it has indoor sensors for temperature and all of that, as well as like commercial buildings, electric vehicle chargers, as well as the power plants and other kinds of factories that may have more sophisticated sensors. So the Internet of Things is like combining all of these sensors and making sense of what's happening, like extracting insights from them. So when you have a smart grid in a city, you have to make decisions based on all of these things coming up. Say, for example, you would want to know how to set the price for electricity charging so that it minimizes carbon emissions overall. So you can make decisions accordingly. And that's where the sensor-driven analytics or data-driven analytics and optimization is a growing area. You can do this for individual units that are listed in here. And the clear example is a smart grid where you have multiple data sets and you can actually do the optimization itself for the system. And as I mentioned, language and climate action is new. I haven't seen many examples of these except for so early warning systems for disasters, like where people disseminate information. But with the recent advances in generative models, I think there's a lot of potential. So one example is this report from IPCC. So IPCC is this Intergovernmental Panel for Climate Change. So they release these climate science and climate action reports every year. Now, this is provided by scientists, read mostly by scientists. So it sometimes makes the headlines whenever these reports comes up. There's headlines from the news articles saying, "Hey, scientists predicted disastrous things in the future." But there's no way for general public to understand what's going on in this IPCC report. They're 400-page long, so nobody else reads it. So there was this scientist who made Chat IPCC. So this is more for lay people to understand, they can interact with this interface, and it's what's going to happen in India in 2050. So you can actually summarize and give it rather than them going through and poring over the reports. So I thought that was a neat example, and I think this area is only going to explode because this is such a new area and there's a lot of potential to look into that. And combine that with other areas like computer vision, I think the possibilities are endless. Yeah, so physics informed machine learning. So, adding physics constraints to machine learning is a new area. So this has been, there was a paper on physics informed neural networks that came out a few years ago. Since then, there were so many applications that have been applied all over different kinds of domain sciences. So I'll give a small example to illustrate what this is. So say, for example, there is an apple tree and an apple falls from a tree. Now, the typical way to do that is, you can use the physics equations and then find out if you want to know where this apple is going to fall on the surface. You can find the initial position, you can do the physics equations, and then you can find, okay, this is relatively the position. If there are no wind conditions, this is what the land. You can also use a machine learning model to fit that. So say if you're dropping this apple from many number of times from this tree, you can fit an equation and then say this is the initial position and this is the final position, run the model. The model would do it. If you have enough data points, it will get the accurate location for that particular tree. But say you have a new tree now. This tree may or may not be in the vicinity of the old tree. So whatever model that you develop may not work on this tree. If it's very close to it, then say that you have the initial and the final position, that may still work. But say this tree is located on a hill or an elevation, then you cannot guarantee it. You can even give an opposite result where the apple may fly upwards. So that's not physically consistent. So there's another way to make this work. So what you do in typical machine learning domain is you drop the apple from another tree 10,000 times or 20,000 times, then augment this machine learning model and make it work. But then you're considering 1 million trees that you want to look into. That's not a feasible approach. That's computationally intractable. So you cannot go and train this data point on every apple tree. So that's where physics informed machine learning comes in. So we introduce a very simple concept. In this case, we introduce gravity. We say the final position is always lower than the initial positions. It's as simple as that. And it immediately generalizes to all the trees with falling apples. So we don't need to train 10,000 data points on each tree. So that's what we say when we say, adding physics constraints will generalize better, and it requires a lot less data, a lot fewer data points to actually train it. Now, how it applies into climate action. So as I mentioned, the climate models here, these are very highly resolved. For each grid, you have so many physical equations for ocean, atmosphere, cryosphere, and you name it. So they have teleconnections, they have to be resolved. So just by using the data points, like you cannot generalize enough, or you need a lot more data points to actually gather the physics. So, and also, like I mentioned, the running each climate model takes weeks to months. So it's impossible to generate all kinds of scenarios for machine learning training. So that's where we introduce physics in there. It can be as simple as saying, oh, the rainfall could not be negative. So it has to be either 0 or positive, even simple constraints like that. So it will give the results that are physically consistent. It will converge faster, and it will train more easily. So this has been used in weather forecasting and also the climate forecasting. So weather forecasting is like 1 to 3 days, and then like climate forecasting is like a year to decades. And they all benefit from these physics-informed machine learning models. With that background, I will go into this project called AI Vito. So this is a hybrid AI framework. When I say hybrid, it's a physics-informed AI framework to capture the effects of cloud properties on global circulation and regional climate patterns. And that's a mouthful of titles, so I'll explain what that is. Before that, so this project was funded by DARPA, which is a advanced research project agency from Department of Defense. They wanted to know the climate tipping points and what are the effects of climate intervention. So when you look up the sky on any clear day, you will find these two types of clouds. So the first one is this fluffy white clouds. It's called stratocumulus clouds, and it's usually found in the lower atmosphere, and it reflects sunlight. So it cools the atmosphere in general. Then you have other types of clouds like the breezy, the wispy clouds, the one on the right. They are usually found in the atmosphere. It absorbs sunlight, so it more leads to more warming. Now, what this means is the clouds have a role to play in what the local temperature is. Now, this is very ideal because, when we think about clouds, like how does it impact global climate? Like I mentioned, surface temperature is one. It also affects precipitation, as we know. And all of these, more advanced climate terms that I'm not going to go through it right now. So our goal was to can we construct a relationship between clouds and climate response? So this is what we started going off with. And the reason behind that was this application called marine cloud brightening. So just focus on this top right image. What you see here is the satellite data of ship tracks. So what they discovered a decade ago is like when the ships, traverse across the ocean, they have these sulfur particles that are emitted by the fuels. And when they reach the clouds, these sulfur particles, they lead to more reflectivity. And then that's why you see these cloud tracks. And why this is appearing is it is locally cooling the climate. That's why we see these kinds of reflective tracks in the satellite data. Now that gave an idea to people like, okay, does that mean can we actually cool the clouds or cool the place by reflecting the clouds more? So that's why this technique became this called marine cloud brightening. So what it means is like, can we spray salt water like seawater into the boundary layer, so it goes to the atmosphere and then it cools the climate. But then, it comes under geoengineering, so it's very controversial. So there's a lot of questions on what will happen with its deployment. But there are also another school of thought saying like, okay, this will help avoid certain, drastic tipping points. It will help avoid Earth going into the cliff of climate change. So how do we optimize it? Can it stabilize climate? Can we, develop some counter strategies? So these are the things that we started with when we started this project. So I'll just focus on what these three images means, and then I'll come back to the text. So what here you see is like you brighten the clouds in this Southeast Pacific area. That here we see the temperature differences. So blue is cooling and then the red is warming. So we see that wherever you brighten directly, you see that it's cooling the Earth or cooling the region. Whereas you can see the Northeast in the US is warming up, and then the Japan and the Eastern China is warming up, and it's cooling in other areas. So there's like all sorts of effects. And similarly, if you cool the Northeast Pacific region, you can see the warming and cooling trends. And most importantly, if you cool the Southeast Atlantic region, like along the African coast, there are warming trends, but look at this. Specifically, it warms the Amazon rainforest area. So that means the drought might happen. So these results are generated from climate models. So what it meant is generating just this one scenario took several months. So you can think of that. If you want to look at all the possibilities, it's going to take a really, really long time, and we may not even get there. And also what it shows is it can give dangerous results. Like, you can say like, oh, I want to cool the region of Africa, but then these are unintended consequences. So we want to avoid those things. And that's where AI-BDO came in. So I'll briefly talk about the architecture and then go into what AI-BDO did. So we use something called a spherical unit. As you know, like as geoscientists, like we deal with Earth data all the time. Typically, what we do is take it as a 2D gridded data. And here we want to look at all of the global data at once. So we use something called a spherical unit, and we used spherical sampling for that. What it means is we take the 2D data, wrap it onto the sphere, and we use a special sampling to get there. So the details are there in our documentation. I'll share that in a bit. So all you need to know is like we take the individual spatial snapshots of these input and output variables. And in the input variables, you have all the cloud properties. And then the output variables, we are measuring the temperature, sea level pressure, and precipitation. This is what we are interested in. What the cloud properties could do is we can choose places where we can brighten and what it means in terms of these technical terms. And then the output will measure like how much it's going to change in temperature and how much it's going to change in precipitation all over the globe. So this is our ground truth that we trained on. So you can see the temperature, pressure, and precipitation, and then the predictions that we got from AI-BDO. So it's pretty accurate in what we got. The model did a great job in capturing all the connections. This is a time average result. So you can see we tested it for every single time the temporal snapshot, and it did a great job. Now, where it would help is we don't want to replace the Earth system models because, I mean, they are more accurate, so we don't want to replace that. But where AI-BDO could help is like do these rapid prototyping. If you think about the few slides before that I mentioned, running even that one region took several months. But say, for example, if you can pick any region, an AI-BDO generates results in less than 30 seconds. And this is what we're interested in. We want to see the major pattern changes. And if we see something concerning, or if we see something that we want to see, say, for example, it looks like it's not giving that much unintended effects, but it helps the climate, then we want to do a more detailed Earth system model to understand the climate response better. So that's where this one is coming in. And it has been very helpful for scientists to actually rapidly prototype. You can select any region and then you can see what's happening. So one note before I show the demo itself. So there's something called climate tipping points. So just avoid the text for now and then like focus on the blue highlighted area. So this one is the West Antarctic ice sheet. So what I mean by tipping point is it's a point of no return. Say, for example, if the ice sheet melts in the future, then that could lead to 30-meter sea level rise, and that would be the end of the world. So the climate scientists have identified major tipping points. So one is the West Antarctic ice sheet. Another is the permafrost. Permafrost, as the name mentioned, it's supposed to be permanently frozen, but we are starting to see that it's actually thawing right now. And the biggest challenge with that is it actually releases methane. And methane is like 80 times more potent than carbon dioxide. So it would lead to more warming, and there's a feedback loop. And yeah, everything goes to a mess after that. So there are different things, one for biodiversity, the Amazon rainforest, the coral reefs die off, like I mentioned, and all of that. So what AI-BDO could help, or marine cloud brightening could help, is like, say, for example, we want to avoid this climate tipping point from happening. One mitigating strategy is shift the southern hemisphere southwest westerly wind equatorward. What it means is like, well, let's look at the reason why it's melting. They have all these warm winds in the equator. It's coming towards the Antarctica region because of climate change. So one thing we could do is like, push this wind towards the equator or keep it in the equator so that it doesn't come here. And we will choose like cloud brightening regions accordingly, so the tipping point is not reached. So, but then, like I mentioned, there could be other unintended effects. We don't know that. So, but if you want to avoid this tipping point, we could do that with this model, and then we could find out. So there is this documentation. I'll also show the quick demo on that. So the AI beta documentation, like it's there on the this website, aibeta.readthedocs.io. You can go there. This has all the other details. So it has the data sets, the training data, and what kind of Earth system model that we trained on. So we used like 21 Earth system models, we pre-processed it, and we released the sample data because these are huge. So we have some example data sets out there, but if you want, we can release more of them personally to you on the Amazon S3. And this also has a demo notebook that you can go and like practice yourself. So it's a Jupyter notebook, so you can go and run these pre-processing data sets, and then how to load the model, and how to run the ML model and all of that. So yeah, I would encourage you to look into that. And if you have any questions, please feel free to reach out to me. And now I will show a demo of the visualization, and then yeah, we can wrap the talk up once again.
In the left panel, you see the different controls that are useful to operate and visually analyze different components of our project. In the leftmost general control, you can specify the time duration of the month from the loaded data set that you want to visualize and run the model with. We can select the month and the year. In this case, we are selecting January 1900. You can select the projection scheme out of different geospatial projection techniques to visualize the data. We have the input view and the output view. So input view will visualize the 7 different input variables that we have. And the output will correspondingly visualize the output. So in this case, we have not yet run the AI video model. That's why it's empty. So we can go ahead and run the AI video model behind the scene with this month, and we can see a lagged result in the output panel once we update the variables that we have to visualize. The temperature. So besides this instantaneous given an instance and then visualizing the output of our AI video or hybrid AI model, we can also use it to perform different MCB experiment settings and see what are the consequences of performing MCB for the particular months or duration. So to do that, we have to first activate our MCB control panel. Then we have to specify the duration that we want to apply MCB for. So with the starting month and the end month. So in this case, we can select a duration of say 10 years, and then select the end date over here. You can select from January 1900 to the month of December 1990. And we can go ahead and initialize this setting and then select the zone that we want to apply the MCB settings for. So we can apply, in this case, let's apply it for the Southeast Pacific region. And then select the variables that we want to go and perturb or change during this MCB experiment. You can go and specify the exact amount of perturbation that we want to apply. And then update the results. So once we have done that, we can see how much of an effect it has on the input that we are producing. We have not yet run the model. As you can see, for this particular region, we have drastically changed or perturbed the original values for the two variables, shortwave surface radiative effect and top of the atmosphere surface radiative effect. We can now go. So besides this, another important thing to keep in mind during AI-based model analysis and prediction is to understand that we are changing the inputs to the machine learning model. So we will also want to check how much of an out of distribution effect or distribution shift the AI model is seeing. So to do that, we have this panel over here, which checks the distribution view of the data. So for the particular variable out here, shortwave surface radiative effect, we are plotting the density of the original training data set or the original experimental data, and the red dots over here are the 10 years, the months of the 10 years of MCB application, and we're seeing how much shift or new data is the model going to see. In this case, most of these new data points or perturbed MCB data points are within the distribution of the original data. So hopefully it is a good setting to apply. We can go ahead and now run the AI video model. And then on the output panel, we can see the results of before performing MCB and after performing MCB experiments. We can also look at the difference between the two before and after during this time period, the average difference between this time period. And we can see in this region that we have applied extreme, there is a decrease in temperature, overall temperature. Another important factor that we want to model here is the effect of these MCB experiments on different regional climate tipping points. How are they behaving? Is there any risk in some of those regions? So to do that, we have this TP risk, which is tipping point risk. Once we activate that, we can see it in this panel over here. Out of the 7 different regions, what are the risks of this particular experiments on these sites here? So as you can see, in the African region, in the Saheli and the Sahara Desert region, there is an increase in precipitation. In Barents Sea ice, there is an increase in temperature. In the Coral Sea region, there is an increase in temperature. While rest of the others also sees an increase, but it's not a dramatic change in the overall climate conditions because of the MCB. So this offers a nice and helpful tool for modelers to beforehand see what can be the possible impacts of MCB. And
yeah, so I'll share the video also with the group. So yeah, basically we had that in the backend, the model in the backend, and our visualization scientists developed this front end so they can quickly prototype these things and look at it. So one major thing I wanted to talk about before I wrap up this talk is like ethics, bias, and fairness while using AI models. As you saw in many of the things, especially in AI video, is these climate applications do not typically deal with the usual facial recognition or those kinds of ethics, but then we have to be aware of the ethical considerations of regions when we think about it. What I mean by that is the data availability is generally poor in global south countries. And specifically the climate models that I showed, the 21 climate models that we saw, majority of them comes from the global north countries. What this means is they have the initial conditions that prefers them, looks into their regional impacts. And we don't have that much representation of global south countries in detail. So we have to be very careful in doing that. So as a result, while training these large models, biases may be introduced because the data comes from global north countries. And there are initiatives now to give compute credits to global south countries so that they can train their own climate models, but there's still a long way to go. So something to keep in mind, and specifically, projects like marine cloud brightening, the impacts tend to be on global south for the most part, whether it's in Africa or South Asian countries. So we need to think about what it means in doing that. And one very important thing, which I always say, is collaborate with domain experts. So as AI practitioners, people get very excited when they look at data, and then they will just fit a data-driven model and then say, this is the input, this is the output, and then look, we did it. But these results have to be verified by domain experts, especially when you're dealing with something like climate change or even healthcare for that matter. So please do not overlook this fact. This is always an important area. And I'll just give a brief spiel about Planette, not too long. So this is a new venture we just started a few months ago. What we do is provide this integrated climate and energy intelligence for the renewable energy sector. So if you think about solar farms, wind or hydroelectric for that matter, they're increasingly seeing all these climate hazards that is affecting these farms. And also the year-to-year variability, the energy production changes over time. It could be because of the, inbuilt climate conditions like the La Nina and El Nino, which makes the flood years or the wind years. But it could also, it's aggravated because of climate change as well. So these developers are facing uncertain futures. They want to know how much energy will they produce the next 10 years or so they can stay in business. So we want to do this energy production and profitability optimization for them, keeping climate change in mind and energy policy in mind. So we want to remove the regulatory hurdles. So we have this SaaS platform that provides all these values as well as provide these energy policy information so they can we reach the decarbonization goal together. So that's where Planette is. And as to just conclude, I'll just give a few thoughts. So this is a problem of our lifetimes, and the time to take action is now. And as I mentioned, there are so many advances in AI recently, and the opportunities are endless. So be creative, collaborate with domain experts to solve these exciting challenges. And some of the interesting links, so there's a group called climatechange.ai. A few of my friends have been running it. So they deal with a lot of, AI applications to climate change. They're always looking for so many enthusiastic young people to volunteer and be a part of it. So please feel free to check out. And also there's this a website called drivendata.org. It's like Kaggle, but then they do provide social good competitions. Climate change is also one of them. So if you want to, get your hands on some climate specific data sets, and this would be a good one to get started with. So yeah, that's about it. Thank you so much for the opportunity, and I'll take any questions.
Thank you, Kalai. This has been a wonderful talk. Round of applause. It's a small group here, so I think we can take questions. You can unmute and ask as well. It should be okay, even if you don't want to type it in chat. We could do either ways. We can do, I think, 5 to 10 minutes of questions. Okay, while that's trickling in, I'll probably ask a couple of things to Kalai. So one is, there's this thing called scientific machine learning. Is that very different from the physics-based machine learning? That's my first question.
Yeah. So that's actually, when we say scientific machine learning, it has a few things in there. Physics-based machine learning is one of the big things in there. And also there's a data assimilation component, which could use physics. So basically what it means is take the data from traditional models, and then they fit a data-driven model on top of it. So people have started incorporating physics constraints or domain-informed constraints in there. But yeah, when you say scientific machine learning, it involves physics-informed machine learning as well.
So is that like a subset, or
yeah, it is a subset. Yeah.
So you mentioned you apply constraints, but the other one could also include that the equations and all of that are influenced by the models themselves, right? So it's just constraints, but models themselves would be different.
Right. So there are a couple of ways people model this, right? The one thing which before the physics-informed machine learning is say you run a traditional simulation model. You get the input and output, and then you fit a data-driven model. That generally works if the conditions are intact. But then, like I mentioned, if the conditions change, then they may not generalize as much. So that's where the constraints are added. The typical way of adding constraint is through loss functions. So if you have a loss function, mean square error, you just add another term and then say okay, constrained by this much. So the example that I gave is the precipitation constraint. You can change all the negatives to 0. So adding a simple thing might actually converge it better, so give physically consistent results.
Okay. My second question is, what is your spatial and temporal resolutions that you have used for the IBDO project?
Yeah, so it's 1 degree spatial resolution, and then we used a monthly temporal resolution for that. So we are looking at climate scale, but we also want to look at the seasonal changes because we want to take in consideration of the seasonal changes. Though we remove the cycles, but we want to make sure that we capture some of it. So it's monthly time scale for the temporal.
And it's for the entire world and for a decade or so, or how long?
Until 2100.
Okay.
Yeah, so we took all the data sets. So the climate models are run until 2050 and some until 2100. So these are just, once you remove the the changes over time, these become just the snapshots that you could train on, because we are mainly looking at how the clouds change the other responses like temperature and precipitation.
So my third question is, really most of the methods that you have talked about are ML models, right? And you had shown this Venn diagram in the beginning where ML is part of AI. So, and yet the systems are called AI systems. So there must be some vision where the difference between AI and AI set, ML set is going to grow in the near future. And we have several students here. So do you, can you talk something about the vision that is there to build these AI systems?
Yeah, I think the reason is like, when initially AI started, right? I mean, ML was a small subset of it. Now I think the ML subset is just growing, and AI ML is becoming almost synonymous. But I don't want to discount the good old-fashioned AI. Yeah, so because they help with decision making. For example, like the AI bureau example that I mentioned, obviously there is this ML component, but then if I am a part of the government who wants to make decisions, then the good old-fashioned AI helps me in doing that. So I assign some kind of an objective. I do that optimization. That doesn't require data per se, but then I know the pathway to get there. So it's, like you say, it's generally overlooked right now because of the hype that's been done by big data and ML. But yeah, they have their role in reach, and people still use it all the time. They just don't talk about it, or they just don't call it AI, they call it optimization. So they just use different terminologies.
And what about the use of IoT and sensors and all of that? So are they all increasingly getting integrated with ML models, and do you have things like that?
It is absolutely, yeah. So even in like weather forecasting, right? I mean, there are all kinds of sensors right now. So one company is tomorrow.io. They have these hyper local sensors, and they predict the hyperlocal weather as a result of it. So they combine that with like satellite data, and then they improve the weather forecasting and so on. So yeah, that's increasingly with ML, with satellite data, it's becoming a huge field in itself. Like IoT is exploding also.
Okay. Yeah, that's quite interesting.
Interesting talk, Dr. Kalai. I have one specific question. You touched upon during your talk on one context wherein AI would help a farmer to understand that if they are growing a particular crop, then maybe after a decade or so, their agricultural land might not be feasible for cultivation purpose. So on this context, I also see that you have touched upon aspects wherein AI helps in improving agricultural practices. So, for example, now you see at present in India, the most pressing topic is the price of tomato. It is so huge, and tomato farmers are asking for security and kind of a Z plus security kind of a thing. That's the level at which things are focused. And a couple of years back, I was in one of the talk where the speaker touched upon how drone technology can be used to do a count of tomato growth or yield and things like that. So what I'm trying to understand is the situation we have ended up today, where tomato is scarce and people are struggling on safeguarding tomato crops and things like that. Do you think AI will reach a position where it can predict such situations, and hence maybe sort of give some sort of advisory or input to the decision-making authority that they have to be careful with the way the crop growth is happening in a particular area, a particular location? Any of these things do you think it's realistically possible, especially in a country like India?
I think that's what people are trying to get at, I think. So, if you look at companies like, Climate Core or Grow Intelligence or Climate AI, that is their dream, right? I mean, that's their vision of like what AI could do in agriculture. Because food security is going to be a huge problem, as you can see. I mean, the tomato prices are up because of the floods in India. Like, this is going to be an ongoing issue all over the world. This is like a extreme event stress, but then you can think about like chronic stress, like drought or like floods affecting the fields. So the company, the Climate Corporation, like it was started, I think it was almost a decade ago. It's one of the oldest climate tech companies that are using AI for agriculture. So the reason they wanted to look at this is they knew that climate change is going to impact agriculture in several different ways. And they wanted to inform farmers, inform the government so that they can prepare themselves to make that transition. So I'm sure several government agencies are looking into this because food security is a big concern when it comes to climate, which means like switching the crops to climate friendly crops, which means changing the diet and all of that. So we don't know, there are so many different branches to this. And also we don't want to not be prepared and get to the stage where something happens like this and then we are caught off guard. So obviously, AI can help with that. And there's also this huge part of policy making that needs to take the insights that we get from private sector and other research institutions to implement it. So there's two parts to this. To answer your question, whether the models can predict, sure, it can do the predictions. It can give scenarios. But then the politics side of it, whether to implement it in the ground is a whole another puzzle to this.
Okay, yeah, thank you. Thanks for the clarity on this.
Yeah, I have one more question, Dr. Kalai. So there's a lot of misinformation also that occurs, right? So are there methods by which, so increasingly because AI is playing a big role in climate action, is there do you also find systems which are able to, or which are designed to counter misinformation? Is there a lot of...
Sure. So if you're talking about the hallucinations from ChatGPT, things like that. So thankfully, I think climate science and AI is relatively new. So it hasn't come to that stage of getting into a deep fake kind of a situation. But I've seen examples where satellite images are being created using deepfake technology. But it hasn't reached a point where people are widely misusing it, but it may happen. It's always a case, right? I mean, the countering adversarial examples of such is a growing area of research, and there are several security researchers looking into that. One method that for ChatGPT itself, to counter hallucination is what they were saying is say, for example, if you inquire something in ChatGPT, if you get the same answer every time, then the probability, you kind of get it. It's the probability of it being true is, more. Whereas it gives a different story every time, then, it's all over the place, then it's not a real answer, it's hallucinating. So it's a very simple metric. People are doing all kinds of research in this area. So one is to look at this probability distribution and finding it. But yeah, so the deepfake, it's pervaded in facial recognition and all of those areas, but it's not as much pervaded in climate science. But I wouldn't, put it behind me. Say, for example, if they're doing these geoengineering experiments, it's so easy to proctor something China did it and then give it to the US and then they are going to be all over it. So yeah, things like that might happen. And and DARPA invests in a lot of adversarial example detection cases. If someone is faking it, how do we find it? Those kinds of research is going on.
Yeah, I would particularly think because there's a lot of, like you mentioned, right? There's geopolitical angle to it, and there's also economic factors, right? Because extreme climate actions also mean that aid is given to a particular country, and so misconstruing things or faking things, and using the deepfake technology, etc., to divert funds, for instance, right? I mean, so
yeah.
and scan.
And you can predict it, like, I know the government can say, oh, there are no floods here, and then just show like a flood prone area to like not have it.
Exactly.
Yeah, I think that's going to be a problem in the future with deepfake, but yeah, we'll have to work towards handling all of that. Yeah, misinformation is a huge problem.
Yes, yes. I mean, it particularly after you started talking about ethics, it just seems like, that also has to be included in the list of things to be considered. Right?
Of course.
So, if there are no further,
I think there is a query in the chat.
Oh, okay.
There's a question.
Missed it. Could you read it out, Purushottama?
Yeah, it is from one Mr. Bharat B. He is asking quantitatively how much clouds contribute to climate change. What is the impact of anthropogenic activities in climate change?
These are really big questions. So I'm not a climate scientist, but I can say the clouds contributing to kind of varies from region to region, and it varies temporally also. So because the cloud variability, the reflectivity changes quite a bit. If you look at the window right now, I mean, sometimes it has dark clouds, sometimes it has brighter clouds, and sometimes it's clear sky. So it varies quite a bit. That's why we wanted to capture all the time temporal snapshots when we train the model, because the changes can be very localized and temporal. That's why we want to do all of these. So that's the first question. I mean, it just means it varies. And the definite quantification, I mean, you could get an approximate number, but I don't know at the top of my head. And then for the second question, anthropogenic, yes, for sure. Like, it is changing. And there's so many studies showing how much it has, it has diverged from the natural path of the Earth. And all of these climate models that I showed in the data sets, it has the one scenario without anthropogenic emissions and the one scenario with anthropogenic emissions. So you can pretty much look at the climate induced or the anthropogenic induced climate impacts because of that. So again, I don't know the number at the top of my head, but you could look up many journals, and there are so many discussions on that.
Okay.
I think that's all the questions we have.
So thank you, Dr. Kalai. I think we can. Bharat, do you want to talk?
Yeah. Thank you, Dr. Kalai. Wonderful to hear you, and thanks for being opening up a new area of research and the area to look into it in future. Thank you very, very much. Wonderful hearing you. Best wishes to you.
Yeah, so I think we can wind up the talk. Thank you again, Dr. Kalai, for accepting our invitation and being a part of IEEE-GRSS Bangalore section for a short while. But yeah, we look forward to working with you and interacting with you in future as well. Thanks again. It's been
thanks for the opportunity, Dr. Jaya. Yeah, and thanks, Gurudatta.
Thank you. Thank you. Thanks a lot.
Yeah. Thank you, everybody, for attending. We'll wind up the talk, and the talk will be put in the YouTube channel maybe in a month or so. Please be patient with that. Thank you, everybody. Yeah, have a good one. Bye.